Hello! Today's first of two little videos is all about evolutionary time, geologic time, and how much time it took for the Earth to get to be what it is today. So this first little part just talks about kind of the origins of the Earth, a little bit about origins of the universe. We're kind of going back into some Earth science stuff. And then the second half of it talks a lot more about truly our ideas for the origins of life. So we're kind of a little ways away from that yet, but I figured I'd give you a little bit of background on origins of the Earth before we kind of moved into the whole life part, because it's always a question that comes up. So, in terms of what's happening in here, basic assumption: origins of life on Earth here on our planet can't be older than Earth itself. Even if you're talking about life maybe coming from somewhere else in the universe, life on Earth has to be associated with, I don't know, Earth. Kind of would make sense. It's kind of stupid otherwise. In terms of what we know about our universe, though, we know a few things. Number one, we know that, well, actually we know more than a few things, but we know that Earth is about 4.6 billion years old, or young. There's types of rocks and things like that. There's evidence that we have to kind of support that idea. We know that the universe itself, the galaxies and things like that, are in the range of 10 billion years old. How do we know this? We know this from something called the Hubble telescope, and this is the thing that you can see down at the bottom. It's been a satellite that carries the telescope. It's been in space since 1990, still going strong. They've done some retrofits and things like that to kind of improve the optics on it. But it's given us some of the most amazing views of our universe that we've ever seen before. And one of the things that happened as we're looking at the pictures from Hubble, was something kind of very unique. That when Hubble was looking at very, very distant objects in the galaxy, that things didn't look right. It's not that the pictures themselves were blurry or anything along those lines, but the colors of the light were wrong. They were redshifted, and that's where you can kind of see the title on this. For example, we know that certain elements, and this is kind of what this picture is up on the left here, we know that certain elements, when they give off energy, like sodium, that there's certain colors of light that are always emitted. And you can see this spectrum of sodium that's on here, that there's always a really strong blue line, a really, really huge orange line, a yellowish line, and then there's kind of a paler yellowish green kind of line that's always there. Every time we do this sodium on Earth, we get the same colors. When we start looking at galaxies, though, and other galaxies contain sodium, we see these same three lines, but the lines aren't in the right spot. They're actually shifted over towards the red side. So when they're fairly close to us, they're shifted just a little bit, and you can kind of see the lines are shifted to the right towards the red spectrum. But when we're looking at things really, really far away, those lines are really drastically shifted towards the red, and that's why it's called red shift. It makes sense. And this is a lot like the Doppler effect. The Doppler effect is a sound effect, so that when things are coming towards you, like a siren or a race car, that you get that kind of sound, that the sound pitch actually changes depending on how something's moving. Well, the same thing happens with light. The wavelength of light shifts depending on whether it's moving towards you or moving away from you. And we find that things that are red shifted means that that object's moving away from you. If things are blue shifted, it means that they're moving towards us. So we can actually take a look at our universe, our galaxies around us, kind of tell which direction they're moving. So when they took a look at other galaxies and other objects in the far distance, we kind of realized that Hubble was actually looking backwards in time. Remember, if you're looking at something really far away, light years away, that it means that it took that long for the light to get to us. If something's 1 light year away, it takes 10 years for that light to get to us. The closest star to Earth, by the way, is about 10 light years away. So if we look at that star in the night sky, we're actually looking at light that was created 10 years ago. But things in the far distant universe, things that Hubble can see, can be hundreds of light years old, thousands of light years old. So we're actually looking back in time when we look at, with a telescope like that. Even if you're looking at regular stars, you're looking at objects that may not even exist anymore, I guess, in our sense of time, but that light was actually created hundreds to thousands to even millions of years ago. And so what we see now is that this idea of redshift, when we're looking at things that are coming from really far away, that's a really good picture that universe is expanding. And I like this kind of balloon analogy that's on here, that if the galaxies were closer together, then the universe is expanding, it's getting a little bigger. The universe, these same ones are expanding, they all get further away from one another. And when things are traveling away from one another, we expect things to be redshifted. And again, no matter which direction we look in the universe, everything is redshifted. So it's not like it's traveling one direction, or some things are traveling towards us, some things are traveling away from us. Everything's traveling away from us. And this is really good example of, or good evidence for what we call the Big Bang Theory. I know it's a TV show, one of my favorites, but the Big Bang Theory is the current best model for what we think happened in terms of the universe formed. I'm not very clear on how those first couple seconds, and I guarantee there's guys working on their PhDs in theoretical physics trying to figure this out, but it appears that somehow, at some point in time, about 15 billion years ago, there was some sort of giant matter explosion. I don't know where the matter came from before, how it appeared at that particular time, but it does appear that it exploded, and that through these last 15 billion years, everything has been sort of expanding out away from each other. And again, this is consistent with redshift. It's consistent with a variety of other types of evidence as well. I'm only giving you one piece on this. And if you're interested in a 4, you may want to go look at some of the evidence for the Big Bang Theory, because it's pretty intense stuff. But that idea of studying how the universe started when nobody was there to see it, how do we collect evidence for that? I think it's pretty brilliant scientific method in terms of what it is. This next slide here kind of summarizes some of the ideas about it. So if you're interested about it, you can go ahead and hit pause, kind of read all about it, but it gives you some of that kind of overview in terms of what some of the different things are. You know, that at the very beginning of time, we're talking billionths of a second, that the very first parts of atoms were created. Somehow those atoms started to parts of atoms started to accumulate into very simple atoms. At about a second, the first true elements of like hydrogen and helium started to appear. And then, you know, it took a few more years to even start to expanding out into more exciting atoms like carbon and things along those lines. And about a billion years later, we started to actually get things, you know, a billion years is a long time, things like suns and galaxies and all kinds of stuff starting going on. So it's pretty impressive. Again, you can hit pause, you can read all about this, but if you're interested in this, I would definitely suggest that for a 4 you go back and take a look at some of this idea about how the whole universe got its start. But I'm going to move on to a little bit more mundane about how our Earth got its start. So we know that about 4.6 billion years ago, there was enough stars around and enough matter around that matter started to kind of collect, condense is the term, into these solid balls of goo that we eventually would call planets and things along those lines. But they're pretty old. 4.6 billion years is a long time ago. And that early Earth was really, really very different. It was very volcanic. They would call it the Hadean period, like Hades as in hell, because it was covered with volcanoes. The crust wasn't really solid. Lots of magma, lightning storms, still being bombarded by all that space debris that's all out there, all the matter that hadn't accumulated into the planet yet. So the planet was still getting bigger. But we know that somehow in that early time, an atmosphere started to form, mostly from primitive volcanic gases and things like that. And down in here, you can kind of see the list of sort of things that was in there. There's some nitrogen, there's carbon, methane, water vapor probably. Definitely no oxygen, though, and that's kind of a critical point, because if oxygen had been there, life probably wouldn't be here today, which is sort of interesting. But we know that there was at least some of these kind of hydrogen, carbon, oxygen-containing compounds, but that oxygen wasn't free oxygen. The oxygen was in water vapor and carbon dioxide, things like that. So again, this very early Earth, definitely an unpleasant place to be. No life at this point in time. However, given a little bit of a couple million to billion years, the Earth started to cool down as that crust started to solidify. Things got a little bit calmer. We didn't get hit by as many asteroids and meteors and things like that anymore. And as more of those sort of volcanic gases got up into the atmosphere got thicker, it got cooler, it actually started to rain. And we now have evidence about this time that I kind of show in this picture here, that water started to form on the surface of the Earth. The crust was cooled down enough to hold little ponds and lakes. Oceans came later, but there was definitely ponds and lakes at this time. But it still wasn't a nice place to be. Still, without oxygen, there was no ozone layer, so tons of ultraviolet radiation, lots of energy still hitting the planet, violent lightning storms, we think, other sorts of things added, as I said, excitement to the planet, lots of energy still, not a very calm place to be. But this sort of environment is where we really think that life started somehow in that water. The joke is kind of that idea of primordial soup or primordial ooze, that combination of all those nitrogen, hydrogen, oxygen-containing compounds, not oxygen itself, but oxygen-containing compounds, plus methane, ammonia, and things along those lines, somehow could have combined to create that early spark, that early chemistry that could have eventually resulted in life. We don't know for a fact that this is where life originated, but we have a pretty good idea that there is. Right now, there's about 3 competing hypotheses for how life could have gotten on Earth. My favorite, of course, is the one in the cartoon, that life got here from somewhere else. It's possible, and in fact, I'll give you some evidence in the next video that we do have some evidence that's in support of that. Not life, but some things that supported life maybe did indeed travel here from space on meteors or meteorites. Second idea, and this is the most controversial one actually, is that life could have originated here on Earth, but in some way that we can't see today. And the whole idea of creation or creation stories would sort of fall into this method. We haven't seen creation since we've been here, so that would be that idea of unknown means. Could be something completely different. It could be some other process that we just don't have any idea what it is, that could have formed on Earth a bazillion years ago, and we've just never seen anything like it since. Hard to tell. The third one is the one that we can really study, though, that somehow life did originate here on Earth, that it did originate from processes that we can see today, that we can study today, and that things that we can look at today can give us ideas about maybe what happened in the past. That third hypothesis, the one that life evolved from non-life, somehow here on Earth, from things that are here on Earth today and processes that are similar to today, is the one that's really best suited for scientific inquiry. That's the one that we can study. The other two, especially number two, we can't really study it. We can't falsify it. We have no way of knowing if something different happened. But we can collect evidence to say, hey, yeah, maybe things like that did or did not. So in part 2 of this video, we'll take a look at this evidence, some of the things that we've seen that kind of support that third possibility. See you in class.